So for those who don't know me, my name is Fiona Doyle. I am the Vice Provost for Graduate Studies and Dean of the Graduate Division. And I'm really excited to see so many people here for what I know is going to be a very fascinating, interesting, and ultimately exciting afternoon as we do our final of the Berkeley Grad Slam competition. So Grad Slam is a model that was launched, it's actually 4 years ago now, at the system-wide level. I know this because this is my 4th year in this job, and it was my first year that it started. And oh, is that my phone going? Okay. I'll make rude comments about people who don't silence their phones. Thank you. The concept, for those who don't know, is that graduate students are asked to provide a 3-minute talk about their research with some specifications on the format, how many view graphs, PowerPoint slides that are called now, they can use. I'm showing my age. And the judges will know all of the rules. So they're sort of strict judging criteria. But the reason for doing this is not to torture graduate students, to do something that they sort of wonder what on earth is the point of this. The fact is that as a graduate student, you are often engaged very deeply in research. You live and breathe this. It's kind of becomes your entire existence, or it did, or at least a large part of your existence, did when I was a graduate student. And yet, in order to both convince people to fund you, to convince people that they should give you a job, to convince people that what you do is important, to actually communicate the results of what you're doing, you need to be able to communicate all of this to an audience that, of course, is intelligent, but almost by definition does not know as much about what you're doing as you do, because at this point, you are the world's expert in what you're doing. And so this format is to give you the chance to actually hone your so-called elevator skills, although a 3-minute elevator ride suggests a technological breakdown that I would hope hasn't actually happened. But that's kind of what we're going to be doing. Now, the way that we run the competition here at Berkeley in order to select a finalist for the UC system-wide competition is that students from across the campus were invited to submit videos. And these were judged by a faculty subcommittee of the Graduate Council. And I'd just like to call out, although he's not prepared for this, my colleague John Battles, please stand up. So John and his colleagues have looked at all of the submissions, so thank you very much for all of that work, and have selected the finalists from whom we'll be hearing today. So thanks very much for your hard work. So we have 10 sort of semi-finalists, they're finalists of the Berkeley competition. We're going to hear from them today. The third, second, and first place winners will be receiving awards of $750, $1,000, and $3,000 respectively. So that's the motivation, another motivation for students to compete. But money is not to be sneezed at. And then the first place winner will be representing the campus at the system-wide competition at the, it's going to be at the LinkedIn again, right, Liz? Looking over there, at the beginning of May in San Francisco. So who's going to be deciding who these, who the rich people leaving will be. Well, we have a super panel of judges whom I'm now going to introduce. And I would ask each judge to stand as I read, and it's her name because they're all women. First of all, we have Nancy Olson. Nancy received her BA from LNS with a major in bacteriology. She has been a venture capitalist for 25 years, and in that capacity, she's received a huge number of pitches from people. She is the founder and managing partner of Fog City Fund, which invested in life science and medical companies. In addition, she served as a trustee of Hampshire College, a director of the San Francisco Opera Association, and she has been a board member of Girl Scouts of San Francisco Bay Area. So she does an awful lot of good in the community. In addition to her philanthropy has extended to Berkeley. She's a builder of Berkeley, which is a distinction you get if you're very generous. A Berkeley Fellow, and she received the trustee's citation. In addition to that, she serves on the Graduate Division's Executive Advisory Board, and she's very generously supported activities in professional development for graduate students, which is something that I know will resonate with all of the graduate students who are here. So thank you very much, Nancy. Next, we have Wendy-Coder. So Wendy worked as a primetime anchor and reporter in local, you can sit down now unless you want to stand. I'm not trying to embarrass you, Wendy. Reporter in local television news for almost 40 years, mostly in San Francisco Bay Area. She's won 7 regional Emmy Awards for reporting and numerous Lifetime Achievement Awards. While in broadcasting, she began her trademark series, Students Rising Above, which is a segment that highlights a nonprofit that helps at-risk students who excel in the classroom despite harrowing personal challenges. And I know that many of the graduate students who are here, I hope that most of you have had an easier ride than some of the students whom Wendy has helped. But in your teaching, many of you will have encountered students who've had very, very challenging circumstances, so that I know you'll understand the huge impact that work like this can have. Since Wendy retired, she's still supporting Students Rising Above as a speech coach and mentor. And she also does environmental restoration work. And in that capacity, which is something that I know will resonate with some of the students here, she's restoring a healthy native habitat and reducing the risk of fire by clearing undergrowth in the Oakland Hills. And finally, we have Caroline Winnette. So Caroline received her MBA from Berkeley in 1990 and then became an entrepreneur and an angel investor. She came back to Berkeley in 2015 to become the executive director of Skydeck, which is a multidisciplinary accelerator program. And she's built that network to include 100 teams with more than 70 advisors, more than 300 active investors, and over 20 campus organizational partners. So many, many thanks to you. I know that you're going to have a really hard time of it, probably a harder time than you might have realized. So thank you very much. And Nancy, I believe you wanted to say a word or two from the judges before we got started.
Yeah, I just want to say thank you for having us, and also to let you know we're really excited about it, speaking for all of us. And because of our format, because your time, we're not going to interact with you. And it doesn't mean we aren't interested and we don't care. It just means we want to stick by the rules. So there may be a little time at the end we could talk to you, but just to stick by the rules. That's why you're not going to smile and talk.
Yes, after everybody has finished their talking, we get to socialize, and the judges have to go off and do what I know is going to be really hard work. However, we all have a little bit of work, because one of the features that we introduced last year is that we also will have a People's Choice winner, and I'll be talking more about that later. but everybody is going to have the opportunity to vote for the person who you thought gave the most effective presentation. So with that, before we get going on the competition, I want to introduce a graduate student who was one of the finalists last year, and this is Joan Dabney. She's a doctoral candidate in environmental science, policy, and management, which most of us know colloquially as ESPON. And by coincidence, she's a member of John Battle's lab. So it's not that we're trying to rig the system, actually. It's just that the Battle's lab seems to have lots going on. Joan works on the spread of white pine blister rust and beetles in the Sierra. And she's going to give a few short reflections on what she got out of the Grad Slam competition. Joan.
Okay, I think I'm good. Okay, great. Well, good afternoon, and thank you so much to Dean Doyle and the Graduate Division for having me here today. And congratulations to this year's contestants for being selected to present your innovative research. I also want to take a moment and thank everybody else in this room for showing up. Thank you for supporting these students as they step beyond their comfort zones. We are here today not just to practice giving speeches, but to take a stand and remind everyone that we are relevant and critical to the betterment of our society. So thank you all for making Grad Slam a success. A year ago, I was sitting exactly in those chairs, and I wasn't paying attention to anything else but the pounding in my ears and the knowledge that somehow I'd gotten myself into another situation where I could horribly embarrass myself. But thanks to a newfound sense of boldness, practice, and the knowledge that my research was important, I faced my deep-seated fears of public speaking. Although I was selected as the second-place finalist, I'm here to remind you that it really doesn't matter who wins or loses today. What matters is that you had the initiative to think about how your research fits into the bigger picture, how your work might be useful, inspiring, or important for somebody outside your field. And this is incredibly important, it turns out, in today's world. As many of you know, the ivory walls around us are being challenged. The scientific process and the recognition that facts are often evolving is unsettling to the public. Many who were never given the opportunity to join the academic system are rightly bitter. And who has the power to produce knowledge is justifiably being called into question. This public distrust can translate to a decline in economic support. Almost every state has cut funding for higher education since 2008. This includes California. The UC system educates more than 230,000 students a year, yet continues to see funding cuts as it takes on more students. To make matters even more complicated, mass media and technology are changing public consumption of knowledge. With so much information out there, it's really hard to digest. And consequently, bite-sized amounts of information will be an important avenue for the dissemination of research in the future. Traditionally, researchers haven't had to directly interact with the public. It is now becoming more imperative to do so. This became very clear to me recently. As a Grad Slam finalist, I was honored to be invited by Dean Doyle to accompany her to Sacramento for the annual Graduate Research Advocacy Day. We spent a full day meeting one-on-one with various lawmakers. And though I was very excited and honored to represent UC, I also felt slightly uncomfortable in my new role as a science advocate. I secretly worried that maybe it represented me selling out, or that somehow my research would be compromised because I was distilling it down into these digestible facts. But as the meetings progressed, I began to see how important my role was. Lawmakers and their staff have only so many hours in the day, and they still have to pass bills and implement policies. If the producers of knowledge are just communicating with each other, very little of this research will make it outside into the hands of the people who need it. I realize it's partly up to us, students and researchers, to make sure that our most recent findings are communicated to the right people. And this is no small task. It requires change, and we all know we love change. It requires changing our perceptions of advocacy. It demands relearning how to communicate our science. It also means knowing who to reach out to in this vast public arena. The hardest part for me personally is that it requires stepping into a space where I feel even more vulnerable to criticism. All of these are skills, yet they haven't traditionally been taught to students. For those who are making the transition, including these amazing Grad Slam contestants, it takes a tremendous amount of bravery. Ultimately, research is the best tool we have to solve the many pressing issues faced by the 7.6 billion people on this planet. But we are at risk of losing relevance and support. I am hopeful, however, because we are starting to develop new communication tools and organizing public events like Grad Slam. We're also harnessing the power of our diversity, the diversity of our research and the diversity of our student body, and reminding the public that knowledge is produced by the people, for the people. So, hats off to you, fellow students, for rising to the challenge. With that, I say, break a leg and go Bears.
So just before we hear from our contestants, which of course is the moment that we're all waiting for, except for the contestants, I wanted to do a little bit of housekeeping. So each of you in your program will have received should have an insert, which is a ballot. So this is where you will, at the end of the contest, and please not before, sort of anything that we see being written on before the end is going to be disqualified. This is where you get to judge the People's Choice contestant, and our staff will be collecting these. You'll also see from your program the names of the contestants and their smiling faces, which is lovely. And you might be wondering, well, who decided on the order? We decided this year not to do alphabetical order or even reverse alphabetical order because I know my last name is D, and I always have to go early, with things like this. And then there are people who are kind of always last. And so we decided to randomize. And when we actually get to the topics, you'll see that this truly was random because it's not necessarily the order that we would have chosen. So it really is random. In between, we'll be calling up the contestants one by one. And then once they've finished, we will then give the judges up to 3 minutes to write notes about each contestant. While they're doing that, I'll have a conversation with each contestant where we'll learn a little bit more about them. We don't do that before they start because they need to be all psyched up in their heads about going into their 3-minute talk. One of the reasons why we need to let them kind of hit the ground running with their talks is that they're going to be judged on intellectual significance, appropriateness, clarity, organization, engagement, delivery, and visuals. But this 3-minute talk is really important, and they're going to have points deducted for every 3 seconds that they exceed their 3 minutes. And that can be important. So they have all practiced, and so on. We don't want to mess them up in that. So with that, I think we can get started. And the first contestant, and I realize I forgot to check with our contestants on how to pronounce their names, so that later on they'll be able to correct me if I happen to inadvertently butcher their names. Is it Kelsey? Kelsey, is it Adam or Adam? Adame. So thank you. You see, this is clearly not rehearsed. So Kelsey is doing a master's degree in nuclear engineering, and without further ado, I'm going to invite Kelsey up to give her talk. Yeah.
When people hear the word nuclear, what tends to come to mind are things like radioactive waste, the Fukushima disaster, or even the ever-present threat of nuclear war. And this is a shame, because the fact is, nuclear science has contributed enormously to our lives, with perhaps nowhere more overlooked than in the medical field. You can thank nuclear medicine for treating 1 in 3 cancer patients in the United States. And our project with Berkeley's Nuclear Engineering Department aims to make these treatments applicable to a wider range of procedures and available in more hospitals more often. Let's first dive into how this works. These medical procedures require radioisotopes. Radioisotopes are unstable atoms that decay over time, releasing energetic particles. For diagnosis, these particles can be detected using cameras, creating a detailed map, like this one, of the affected area. For treatment, these particles can be harnessed to attack and kill cancer cells. This crucial industry, however, is facing a problematic future. The problem is that we obtain these isotopes from a select few nuclear reactors. These are massive, expensive facilities, and being fission reactors, they generate nuclear waste and are the subject of proliferation concerns. Alarmingly, while the demand for isotopes continues to rise, these reactors are reaching the end of their life. For example, the Chalk River reactor in Canada, which supplied a third of the world's medical isotopes, shut down 4 days ago. And with supply limited to just a few producers, the radioisotopes that they happen to make have shaped our treatments, instead of the treatments patients need shaping which isotopes we use. Clearly, we can do better. So this is where we come in. Our research uses a device that leverages fusion rather than fission to get these special isotopes. This means slamming particles together instead of splitting them apart. And while nuclear reactors cost billions of dollars, our technology costs around $250,000. This incredible device is called a neutron generator, and amazingly, it's the size of a mini fridge. So instead of flying time-sensitive decaying treatments from reactors to hospitals, we can now make them in the room next door. It's like having your own ice cream machine instead of having to transport a dripping cone across a desert. Our prototype device has shown the proof of concept needed to create and extract these novel isotopes. My role has been in accelerating commercialization, analyzing the technical details of the neutron generator, and aligning these with the needs of hospitals. With this solid foundation, we continue our march towards improved device designs. We're showing that even the smallest particles can have the biggest impact.
So thanks so much, Kelsey. It was a great start. So, first of all, let me ask you, where did you grow up, and where did you do your undergraduate work?
I grew up in a small town in New Mexico. And I also
near Los Alamos?
Not near Los Alamos. I mean, that definitely had a large influence on what I'm interested in. I grew up near Albuquerque, and I went to undergrad in Socorro at a place called New Mexico Institute of Mining and Technology, and I studied physics and math there.
So did you come to this project from the perspective of being interested in the nuclear engineering side of it, or was it more the application of the physics and the math that really kind of intrigued you and got you involved in this?
Yeah, I really liked the idea of a project that kind of brought together these physics ideas and really did something that is like changing people's lives instead of just, being really theoretical as I had been in my past.
And in the medical imaging, is it the neutron or the helium that's actually used as the energetic particle for the imaging? Or
yeah, so different diagnosing uses different particles for these images. So when these isotopes release like beta or alpha particles, and that's what we're.
So you said that you were particularly interested in the commercialization of this.
Yes.
So is there currently any commercial equipment available, or is this something that is currently conceptual?
Yeah. So
and if so, kind of how far off is it before we'll start seeing these neutron generators in our doctor's offices and things like this?
So we have a neutron generator here at Berkeley. I imagine it's going to be hopefully a few years before we start seeing them in hospitals. Right now, sometimes they use cyclotrons,
but those are also very large and expensive, and we're hoping to make this sort of the norm.
Did you know that we used to have a nuclear reactor here at Berkeley?
I did. I did.
Yes, I better around campus, but not having that. So, did you always want to go into kind of a technical field, or did you kind of come to physics and math as you were coming to the end of high school?
No, I've always been really interested in math and physics, and that's what I've loved. And just recently I've gotten more into like communicating these ideas to the public.
Yeah.
Because I think that in academia these ideas kind of like stick in our like homes and we don't spread them very well to the public. So now I'm getting more involved in making sure that these ideas are communicated.
Uh-huh. And so how are you finding California compared to New Mexico?
I like it a lot better.
Oh, you do?
But there are things that I miss about New Mexico.
Uh-huh. And do you find, I was going to ask, what do you do in your spare time? I suppose the first question is, do you have any spare time?
I mean, not really. I play piano.
Oh, you do? Uh-huh.
Hanging out with friends, exercising as much as possible.
Uh-huh. Have you got to do much sightseeing around the Bay Area?
During spring break, I went to Big Sur.
Uh-huh. It's pretty awesome, yes. Yeah, there isn't cliffs and things like that in New Mexico.
No.
Are we ready? I thought we were just, Lynn sometimes kind of raises her hand. I thought that, you want to
continue with my life story?
No, often I'm having such a good conversation that she's wildly gesticulating at me, saying, we're ready, we're ready. Are we, okay, right, I'm thumbs up otherwise. Well, thank you very much.
Thank you.
Thank you for So just to demonstrate my point about the fact that our contestants were randomized, our next contestant is also from nuclear engineering. And for those of you who aren't familiar with engineering, as I am, because I'm a professor of material science and engineering, nuclear engineering is actually a tiny department. So the statistical chances of the first two contestants being from nuclear engineering are exceedingly slim. But nonetheless, our next contestant is Maria Simonovskaya. Is that approximately? Thank you. Maria is also from nuclear engineering. She is in the PhD program and is in her 4th year there. So join me in welcoming Maria.
Look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. With these words, Stephen Hawking inspired me to ask questions and come to grad school. I quickly realized that there are many gaps in our understanding of the universe. One example is we don't understand how our galaxy is held together. We can measure how fast everything is moving, and we know that when something is spinning, it tends to fly outwards. We also know that gravity pulls things together, but it turns out that we don't see enough stuff in our galaxy to have enough gravity to keep everything from flying apart. This means that either our idea of gravity is wrong, or there's a bunch of matter that we don't see. We call this dark matter. A second fundamental problem is in particle physics, in which we predict the neutron to have a characteristic called an electric dipole moment. Experimentalists have tried to measure this, and they keep measuring it to be much smaller than what theorists predict. This size difference is like expecting to see the volume of the San Francisco Bay, but only seeing the volume of a blueberry. Theorists have many ideas for how to solve these two problems, and the simplest idea solves both of these problems at once. This involves introducing a new particle called the axion. This particle is appropriately named after a cleaning product, because if it exists, this terrible mess in the standard model of particle physics and in our model for how galaxies move will be cleaned up. Theorists are very clever people, but the problem is they don't all agree on how to solve these problems. So we need experimentalists, like me, to help sort things out. I'm working on an experiment in collaboration with groups at Yale and Colorado to detect the axion. How it works is we have a cylindrical copper resonator that can pick up a certain frequency, like a radio. We can tune this frequency, and at some point, we expect to hear the axion signal. This can happen because the axion is a particle that acts like a wave with a certain frequency. We don't know what the axion frequency is, so I need to be creative in designing new resonators to reach a wide range of frequencies. Detecting the axion will not only help us understand how our galaxy is held together, or why we're seeing a blueberry instead of seeing the San Francisco Bay. It will also give us the knowledge to tackle other problems in our understanding of nature. Thank you.
So, thanks very much.
Thank you.
Now you can relax.
When I sit down, maybe.
So, what was your story? How did you get in? Did you get interested in axions, or were you interested in something more general that then led you to axions?
Yeah. So I guess in my family, right, my grandmother was a physicist, and my mother was in physics, and so I wanted to go into physics, although my mother told me
You weren't a rebel?
not to go. No, my mom told me not to go into physics because women, it's not a good place for women, actually. Right, my mom told me this. Because from her experience. But my dad told me that if I study physics, then afterwards I can study whatever I want. So that's how I started physics, and then I just continued. And it's actually very exciting. I'm very excited about it.
I was a rebel, and
Okay.
sort of did things that I was told not to do. And I come from, well, my mother and an aunt were teachers, and I was absolutely adamant that I was not going to be a teacher. So guess where I end?
Okay. Yeah.
Sometimes life has a way of sort of basically messing with your decisions and saying, you were wrong. And where did you grow up, Maria?
So I was born in Russia, and then I moved to the South Bay in elementary school. And so I grew up in the South Bay.
How
and
old
then
were you?
I was 7. Yeah.
But
then I went back a lot for the summers because my parents were so busy, so they sent me off to my grandparents every summer.
They probably wanted you to keep in touch with
the language and stuff.
So, you must have some sort of pretty interesting contrasts in terms of two different cultures.
Definitely.
Any sort of thoughts that you'd like to share with us?
Okay.
At the moment, we aren't having any trade wars with Russia.
Well, okay.
Well, hold on.
Right.
But, you don't have to go political. I'm actually really interested in kind of culture, particularly educational systems, and sort of the expectations that kids in the two different cultures have.
It's interesting.
You've observed.
Right. So I feel like actually, I don't know, I don't want to insult anything, but I feel like the average education in Russia, right, is pretty good, right? The standard is very good. But here, the, possibilities are better. And so like the standardized tests, right, like the California exit exam, right? One of the questions was like 2 + 5 = A, 4, B, right? But the actual opportunities that people get here, right? It could be a lot higher. So at least in terms of education, it's like really accelerated here, but the average level is kind of left.
Uh-huh. I can tell you, having been educated in Britain, that I was astonished at the differences in approach to science education in Britain and the United States.
Yeah, that's true. Here, people don't have to take physics at any point in their lives.
No, I started physics when I was 12.
Right.
It was kind of just one of those things. It was kind of, physics for 12-year-olds. But physics for 12-year-olds is actually a lot of fun.
Right. And everything, I feel like everything is physics,
Yeah. I did until I got to a point where I couldn't understand the physics anymore and had to do engineering. So I congratulate you on still being in the physics. So, okay. Apparently we're done.
Okay.
Just
nice to talk to you.
Thank you very much. Okay, and just proving that we really are randomized. It's not that all of our contestants are from engineering, but our third contestant is also from engineering. But this time we have a fifth-year PhD student from electrical engineering and computer science, Daniel Drew, who is just getting mic'd up, which shouldn't be any problem for him because he's in electrical engineering and computer science, and so should be able to deal with the technology. And please join me in welcoming Daniel.
Thank you. Over 100,000 people lost their lives when an earthquake rocked Haiti in 2010. Before that, 2004, almost 300,000 people were killed in a series of tsunamis around the Indian Ocean. Much closer to home, 21 people lost their lives in a series of mudslides outside Santa Barbara, California, just the other month. Imagine a ruined city, rubble and debris as far as the eye can see, infrastructure like cell service and internet wiped out. In a situation like this, a first responder struggles to find out where they are needed most and where the victims that need help are located in the first place. Humans just aren't very good at navigating this kind of environment. There is, however, life on Earth that is. I'm talking about insects. Creeping, crawling, buzzing insects periodically infiltrate every corner of the Earth. Although individually small, insects can work together in swarms to do incredible things, like build structures tens of thousands of times larger than themselves. So now imagine you're a first responder. You've come to the base of a collapsed building. Working by flashlight, it's hard to see much more than the dust hanging in the air. Now out of your pack, you pull out 100 insect-scale robots. And after tossing them out, they quickly scurry, hop, and fly off in all directions. Infrared cameras on each robot look for signs of life. When one spots a survivor, it sends a message back to you over a wireless mesh network, where each robot acts like a little router. Now, a pair of flying robots glowing like fireflies leads you on to the victim's location, while a group up ahead clears out all the debris in your path that it can. I think that the future of tools look a lot like gnats. In my group, we're building these autonomous micro-robots out of silicon. Why silicon? Well, it lets us use the same manufacturing techniques already used by the semiconductor industry, the same industry that brought us Moore's Law and a flood of cheap and powerful computers. We envision these robots as being so plentiful that they are practically disposable. These aren't million-dollar androids. These are robots much like an insect. Our lab's working on a number of mechanisms for flying, walking, and jumping at the micro scale. Some of these designs are biomimetic, which means that they seek to replicate what's already found in nature. Others are not. Entirely new engineered systems that will create millimeter-scale robots with capabilities unlike anything found in the natural world. I personally work on flying robots that use ion thrusters for propulsion. That means that they move completely silently and with no mechanical moving parts. They have more in common with a UFO than a bumblebee. All right, the first tools, they helped us work without damaging our bodies. The next, they amplified our strength. They made tasks easier. Modern tools, they use computation to perform precise, repetitive tasks. In the future, we'll take it another step further. By imbuing the tools themselves with the degree of autonomy, we become more than just operators of those tools. We become collaborators. So now I have to ask, what would you do with a pocket full of insects?
So thanks very much. And actually, I was actually thinking that my first question was going to be, what was your last line? So you posed it as a question. But there have to be many, many other potential applications for robots like this that are basically so small but cheap and disposable.
Let me tell you, it's great to hear you say that. I think that a really emerging application is in agriculture. So using drones in agriculture is being pushed pretty heavily right now for commercialization. There's more fun ones like swarm interfaces where we kind of interact with these robots in our daily lives and how can we use them as displays or maybe haptic feedback. So yes, there are a lot of applications.
Are there also sinister ones or potentially sinister ones in terms of privacy is something that many of us have been thinking about recently?
I'll tell you a secret because you asked. These robots are really bad right now.
Okay,
They're really bad.
This is really secret.
Yeah. They don't work very well at all right now, okay? So when that bridge comes, we'll cross it. But yes.
Uh-huh. So what? That's good to know. So what's your dream insect for first response?
Mine aren't like insects, so it's kind of cool. I think that killing mosquitoes and whatever gets us to do that is pretty cool. Bumblebees have a lot of kind of colony behavior that's interesting. I think that the most impressive are actually the leafcutter ants that I showed at the bottom left. They have specialization even within the ant, so each ant can do something a little bit different. And they work together, but not just like 100 of the same ants working together. It's 100 different kinds of ants, and that makes them able to do more impressive things. I think that's cool.
So, I mean, is that kind of social behavior where there's differentiation of task? Is that something that there's the capability of actually building into robots ultimately?
I think so. So that's right. Those ants are called social insects because they do things like that. I am planning on starting research in that exact area of kind of specialization at this centimeter-millimeter scale to see where we can take that. Yeah.
So what was your background? I mean, did you grow up collecting bugs as a kid, or were you kind of a geek who suddenly realized that actually these annoying little things actually were potentially quite useful?
I grew up reading a lot of science fiction and not really, maybe playing with Legos is traditional. Yep. I didn't do that much engineering or math or science until actually middle of college. I decided to switch into engineering when I realized that kind of engineering is the field that lets you make these cool dreams that you learn about in science fiction come true a little bit closer. So now I'm like working on science fiction. It's pretty cool. Yeah.
Okay, well, thank you very much.
Thank you.
So while we do the mic change, let me briefly introduce our fourth contestant. So now we are doing something different. David Wheeler is a fourth-year PhD student in ancient history and Mediterranean archaeology, which is a small graduate group that does some very interesting interdisciplinary things. Take it away, David.
When I try to explain the impact of visibility in ancient society, I turn to images like this one. Now, this is an image that makes a minority identity, in this case queerness, visible, an action which acknowledges and normalizes queer existence. Regardless of how you feel about this image, it has the power to make queer people feel seen and welcome in this space. Now, just like the queer community of today, the Greek diaspora of ancient Egypt was also a minority community, struggling to find its place in a dominant foreign culture. Now, this may run counter to the image that you have in your mind of ancient Greece, an image put there by museum exhibitions and summer blockbusters, which celebrate the cultural achievements of this great civilization. It certainly runs counter to the narrative presented by ancient Greek historians who seem to suggest a relatively easy transition for those Greeks who chose to settle along the banks of the Nile. However, if we turn to the graffiti which this community leaves behind, a very different narrative emerges. Now, previous scholars have mostly looked to this graffiti to reconstruct historical events, but my research shows that there's a lot more we can learn from them. All along the Nile, the Greeks leave their mark at some of the most famous Egyptian monuments. Now, at some sites, they just leave their names, a process which inscribes historical presence and memory into the landscape. But at other sites, they leave behind poetry, projecting a sense of Greek literature and genre. Or they use graffiti to imprint their own mythology on the landscape, or declare their devotion to some Greek or Egyptian god. But the result is that they make their Greekness visible in a landscape almost entirely devoid of Greek temples and sculptures. These graffiti are some of the only physical, visible manifestations of Greek culture. So the graffiti, rather than confirming the narrative of ancient Greek historians, instead suggests a community struggling to make itself visible, and both literally and figuratively carving spaces for itself in an Egyptian landscape. Now, my research is important because it provides us with a way to understand this community, which has been largely neglected by scholars, but it also creates space for different kinds of narratives about the past. In a day where this idea of the superiority of Greece and Western culture is used by white supremacists and Islamophobes to justify their intolerance, by queering the Greeks, we problematize this narrative and we replace it with one of Greeks negotiating their identities alongside their Egyptian neighbors. And in a day with border walls and travel bans, that kind of visibility can make all the difference. Thank you. All right.
Thank you, David. So, I mean, it's fascinating to me. I thought that graffiti was kind of an sort of an exhibition of bad behavior on the part of modern society. So, all of my kind of put-downs of what's the world coming to are apparently sort of inappropriate.
I hope so. For my research sakes, I hope so.
So, sort of two questions sort of come to mind immediately. Did the ancient Greeks use either jokes or obscenities in their graffiti?
So, in one instance, we think that they may have. Actually, this one right here, this is actually a perfect segue. At the very bottom.
I mean, don't go X-rated. I'm just in general terms.
But, yeah, essentially we have, like this graffiti, we may have a joke where the person that says this graffiti is carved by me and also by my axe. But the name is potentially, a name in sort of a different sort of cultural group at the time. So he says, I carved this, and so did my axe, son of nobody. So we do get some sort of hints like that they are sort of making puns and jokes. But usually it's not quite as funny.
I mean, not knowing much about Greek, other than what I learned when I was way too young to appreciate it, and then it was all which wars were fought when. Yeah. I mean, is humor an element in kind of broader Greek literature?
Yes.
I mean, sort of, how pervasive is humor as a human quality?
I mean, the Greeks are the ones that invented comedy, so
but I don't always find comedy fun.
That's true. Well, I mean, the thing that's so interesting about specifically Greek comedy, thinking about especially old comedy, that's what I like, is that, one of the reasons why it's less funny to us is it is so culturally specific to them. They're making fun of people who, are politicians of the day, that it can be hard for us to kind of tap into that humor or to those puns. But yeah, they're doing essentially the same thing that SNL is doing. And some of that does start to pop up. Well, you'll actually have, mostly in Greece, you'll have people who are sort of making fun of people. And it is kind of like the bathroom wall that you always kind of see where someone says, like, this person's the worst, and then someone else is like, nah, and then it just kind of becomes this interesting dialogue. Yeah. Which is one of the real interesting things about this graffiti is that, there is a community dialogue happening sort of across centuries where people return to the same location that someone 100 years ago wrote a graffito, and they leave their mark too. So it's fascinating, at least for me. Hopefully it's fascinating for you too.
So, I mean, do you ever, when you're kind of looking at bathroom walls or wherever, I mean, do you ever ponder what people would infer about our society from our graffiti, and think about this as basically a feedback for validation of your own work and any conclusions that you might draw?
I mean, the one thing that I usually see, again, with sort of even with bathroom graffiti or any graffiti, it is this, this desire to be seen, that everyone, and that's why I start with that first example. And politically speaking, we're operating in a time where visibility is really important for groups who are being marginalized, and being able to make yourself visible has a real effect. And you can see that with that image that I put up there. That was from an IKEA catalog, which is huge. But even with a bathroom wall, just being able to put something up there that says, I'm here, I'm queer or whatever else, it has an impact. And when you walk into that space, you do feel a little more welcome there than you would have normally. So, at least I hope. Although, don't blame me for all the bathroom graffiti. It's not going to be me, I swear.
I have to say, I've never written on a wall. So
well, now you got to try. So this is your homework, everyone. Go right on a wall. It's going to be great.
Thanks very much, David.
Thank you very much.
And our fifth contestant is Alberto Sanchez. He is in his first year of PhD studies in architecture. Take it away, Alberto.
Thank you. Perhaps many of you are familiar with this picture and the story of Cecilia, the elderly woman who failed to restore this religious painting in a remote Spanish village. In the summer of 2012, the story about this failed restoration became viral, and it was covered in media outlets from all over the world. However, no one went beyond the joke. Cecilia was trying to help because there was no one else in her community who cared. Her town had depopulated almost completely. In fact, during the second half of the 20th century, Spain experienced the most extreme episode of rural depopulation in modern European history. This phenomenon occurred across southern Europe, but no other country suffered it as much as Spain. In just 3 decades, from 1960 to 1990, a country the size of Texas saw how more than 3,000 villages were completely abandoned. Additionally, the dictatorial regime of Francisco Franco flooded 500 villages to allow for the construction of water reservoirs. And today, there are about 4,000 municipalities with a population under 500 people, like that of Cecilia. As you can see on the map, more than half of the country is under the so-called demographic desert threshold, a population density value that has been estimated at 25 people per square mile. This is the largest demographic desert in Europe. My research at the College of Environmental Design addresses 2 lines of inquiry. First, how did we get here? Why did rural depopulation impact Southern Europe much more than Northern Europe? Why did it impact Spain more than any other European country? Why did Franco's regime decide to flood all those villages instead of building smaller dams and water reservoirs that wouldn't have required this flooding? Why are people living still today in these areas? The second part of my research is a little bit more complex. Is there something we can do about this? Why are the rural development policies of the European Union failing to revert depopulation? How could those policies be informed by the past of these areas in order to ensure this future? I myself come from one of these villages, a town of 300 people in the province of Zaragoza. But my research is not just about me. It's not just about people like Martín and Sinforosa, the 2 last inhabitants of La Estrella in Teruel. It is about expanding the boundaries of architecture scholarship, which up to date has paid almost no attention to rural issues. I believe that the spatial and territorial implications of this phenomenon are important enough so that we as architects pay attention to it. After all, if architecture is the art of habitation, shouldn't we be concerned when there is no one to inhabit the buildings we design? Thank you.
So thank you very much. It's obviously a topic that you're very passionate about. On the basis of what you've done so far, do you have thoughts on some of the steps that might be taken to reverse the depopulation? I mean, in a world that is so crowded, it seems that, you know, this is just really so surprising, astonishing, you know, when there are clearly good resources.
Yeah, and it's interesting because when you see the map and see the impact of this problem, and you see that these rural development policies that are basically putting money in these areas without reverting the population, what you realize is that the policies must be wrong, because there is public funds that are being invested in trying to promote that people stay, but they are being unsuccessful. So one of the things that I've realized through my research, I mean, I'm a first-year student, so I have a long way to go, is that, for instance, the rural development policies of the European Union are based exclusively on agriculture. Mm-hmm. So agriculture subsidies is the only mechanism that they have to promote that people stay. So one of the obvious questions is, like, why is that? Why are not other sectors being funded or being given subsidies so that people who stay do not have to be farmers by necessity? Mm-hmm. So that's one possibility. But it's really a really complex phenomenon. As I explained, this affects all Southern Europe. No other country as much as Spain is affected by it, but it's like a prevalent phenomenon across like Italy, Portugal, Greece, and of course Spain.
Mm-hmm. And what about infrastructure, roads and rail transportation?
That's also another issue.
Presumably those could accelerate other kinds of work.
Yeah, and it's interesting because this is also an issue of scale. If you compare, Spain is the size of Texas, as I said. So actually distances are not that big. Like my hometown is like 60 miles away from a 1 million people city. But no one will commute for that long. That's like inconceivable. Like commuting for an hour is just like, no one will do that. So I think it's also like a matter of mentality. Like I think the idea of living in like the countryside is not valued by the public. And I'm actually looking at this idea of, during Franco's regime, how the government promoted this idea of the urban as better and the rural as backwards, and how that impacted the public, and considering that living a rural life was worse than living in a city.
Mm-hmm. And what drew you to Berkeley?
Actually, the fact that it's really multidisciplinary, that I took 2 classes in anthropology last semester, I'm taking one in art history now, political science. I can do that here, and I cannot do that anywhere else. So that idea of like being able to really do this, approach this, not just from an architectural perspective, but from a really multidisciplinary perspective.
Well, I hope that you're feeling at home here now.
Yeah, thank you.
Thank you. Oh, I thought that was the drum roll.
That's good.
Our 6th contestant is, of course, special, but all of our contestants are special, so I didn't think we had drum rolls for one in particular. I'm now pleased to introduce Andrea Pickle, who is a 4th-year PhD student in mechanical engineering. Andrea.
We see the consequences of overheating electronics in our everyday lives. Our smartphones tell us that they're too hot. We hear our laptop fans go into overdrive. Or, if we're particularly unlucky, our batteries burst into flames. These are macroscopic problems. We can see or feel them using our own senses. But their origins are at the nanoscale. To put this length scale in context, I'm about 1.6 meters tall. A single human hair is around 50 to 100 micrometers in diameter. Transistors, the building blocks of modern electronic devices, now have dimensions of about 10 nanometers. So that's roughly 10,000 times smaller than one human hair. To solve these overheating problems, the first step is to diagnose them by measuring the temperature of the components that are overheating. But there's a mismatch here. The types of thermometers that we use in everyday life are too big. To measure hotspots that are only nanometers in size, we need a smaller thermometer. In other words, a nanothermometer. In my research, I'm developing a new nanothermometry technique using particles that are only tens of nanometers in diameter. These nanoparticles absorb infrared light from the laser. That's light that has even less energy than red light, the lowest energy light humans can see, and subsequently emit green light. It turns out that the shade of this emitted green light is highly temperature dependent. So, by placing a nanoparticle at the exact location on my sample where I want to know the temperature, I can then hit the nanoparticle with a laser and measure the precise shade of green light that it emits in order to determine the temperature of my sample. Another exciting aspect of my thermometry technique is that it's a non-contact method. That means the nanoparticle sits at the exact spot where I want to know the temperature, but my laser is millimeters away from the sample. That's as if I could place a thermometer the size of a tennis ball on some object whose temperature I wanted to know, and instantaneously sense that temperature using a beam of light while standing 3 miles away. By using a light source that originates far away from the sample, we can test devices in real-world operating conditions, something that's often impossible if the probe has to physically touch the sample. With my new nanothermometry technique, I believe that we can get the green light on nanothermometry by measuring the temperature of nanometer-sized components in order to understand how macroscopic overheating problems develop. We can bridge the nanoscale and the macroscale in order to solve some of the most pressing problems electronic devices face today.
Thank you so much. I have a million highly technical questions buzzing around in my brain, and I'm trying to shut them all off because this is a general audience, and I talked before about the importance of speaking to the audience. So actually, let me start with a question that I asked with the bug robots. There have to be lots of applications for a device like this. I can tell, and I'm looking forward to talking to you at the break about it, I can tell that this is really hard to do. You made it sound simple, but I know it's really, really hard, and thinking detectors and the wavelengths of light and everything else. So we'll talk about that. But there have to be lots of other kind of applications for something capable of actually sort of discriminating between the temperature of tiny features that are very close to each other.
Right, yeah, so I think a lot of the kind of exciting applications are in like the electronics space, as I said. There's also like magnetic recording devices is something that we've looked at. In kind of a different area, you know, people are interested now in like biology, single cell temperature measurements. There's other things we have to consider, like will the laser damage the cell? That's kind of another area where we think there might be some really interesting applications of our technique.
Uh-huh. So what got you interested in this? Were you one of these mechanical engineers who just loves heat? Or did it come from the heat perspective, or was it something else?
Yeah, so I think a lot of people...
There are lots of mechanical engineers that love heat. Yes. I mean, it's just a thing.
Yeah, so like heat transfer is kind of a core undergrad mechanical engineering course. I definitely really enjoyed that. And then I did my undergrad at Carnegie Mellon University, and they happened to have hired like quite a few people in the area of nanoscale heat transfer. So I actually got to take some like classes in that area when I was still an undergrad. That's kind of what got me interested in that area even before I came to grad school and specialized in that.
So at the nanoscale, is heat transfer different? I mean, sort of you can't treat it as a continuum?
Right, yeah. So we end up kind of borrowing a lot of ideas from physics and other disciplines that have really thought about kind of transport at the atomic level. And indeed, there are certain kind of link scales where classical heat transfer laws break down. You have to kind of approach it in a completely different way, which is, I think, one of the kind of most interesting parts about our field.
Uh-huh. So you mentioned going to Carnegie Mellon. Did you grow up in or sort of around Pittsburgh, right?
Yeah. Actually,
or did you come from somewhere else?
Yeah, I came from here. I grew up in Marin County, so just north of here.
Uh-huh.
And then I went to Pittsburgh for 4 years, and then you know, when you're doing all these grad school visits in like February, so you go see this kind of everywhere. I came back here, I remember at the beginning of March, it was like 75 and sunny, so kind of that combined with the research opportunities.
Uh-huh. Is your family still in?
Yeah, they're still in Marin.
Oh, I bet I was going to say, I bet they're really happy to have you, although perhaps they bug you about, why don't we see more?
Yeah, that's nice. I get to see them a lot more than I did when I was in undergrad.
Uh-huh.
It's really nice.
Okay, great. Thank you very much.
You.
So our seventh contestant, just getting mic'd up, is Lilith Acadia, and she is in rhetoric. She's in her 5th year of PhD studies.
I would like to offer you a superpower, a tool you can use to catch lies in conversation, reading the news, even introspecting. I'm interested in a special kind of lie, a pretext. You may call it an excuse or a guise. A pretext is a justification for an action or belief that does not reflect true motives, like fallacies of justification. A pretext can be a white lie. For example, if you say you are going to powder your nose. And pretexts start wars, the classic example being Bush's imaginary weapons of mass destruction in Iraq. Catching a pretext doesn't only give you the satisfaction of calling out a lie, it also opens an opportunity to look for the true motives, understand the situation more clearly, and make stronger counterarguments. My dissertation distinguishes pretext in order to help identify which justifications for ethical stances or actions we might consider just, by first dismissing those that do not reflect motivations of the speaker. Utilizing speech theory and epistemology, I have developed 10 tests for identifying pretext, and I'd like to share 3 with you today. Imagine you are debating women's reproductive freedom with the man who argues that the 10 Commandments forbid killing and life begins at conception, so first trimester abortions and Plan B should be illegal. Since our laws are not based on the Bible, this is an appeal to a relevant authority. Next, you pose a thought experiment. Running to escape a burning building, you can either save 1 5-year-old child or 1,000 viable human embryos. What do you do? If he chooses the child, he is exercising selective enforcement. We might call this the hypocrisy test. Finally, after telling your interlocutor these 2 pretext tests, he retorts, contraceptions interfere with God's will. Keep an eye out for the speaker who jumps between justifications or doth protest too much. Shifting justifications indicate that the speaker is merely throwing out arguments they hope will appeal to the audience. My dissertation offers an analytical tool for lawyers, journalists, teachers, voters, and you to identify when a justification is merely a clever rhetorical trick to strengthen a weak argument or veil a true motive. I hope now you will be attuned to the appeal to selective authority, to irrelevant authority, selective enforcement, and shifting justifications tests, which signal the powerful lie of pretext. Thank you.
So you must get asked this a lot, but I'm sure everybody in the room wants to know the answer, so I'm just going to be boring in asking this question. Has the Trump administration changed the direction of your research? Or did it, I mean, sort of in a way, it kind of came along as, was it like sort of this sudden gift of Exhibit A, Exhibit B, Exhibit C, and so on? I mean, on a serious level, did such an example of untruth and alternative facts actually cause you to think slightly differently about the way that you're doing your research?
I'm sure that there's some term in pedagogy for when you start studying something and then you see it everywhere. And so because I started this project 2 years before I came to Berkeley, actually, I was already cued to be looking for it everywhere, and it seems incredible when I look at the news. And of course, there are examples of my ventriloquist test or selective enforcement test, and yes, it's everywhere. But having already been cued to be looking for it, our world is full of lies, and we just have to know the tools to use to look for them.
Okay, so you know, I'm now thinking, okay, what's she thinking about me? But I'm asking questions, so and nobody's applying your tests to you. So let's sort of let me ask you just a more straightforward question, which I assume you'll be answering truthfully. Where did you grow up, and how did you...
I was born in California because my father was also doing his PhD at the University of California.
Oh, really? Wow.
And then I went to Smith
awesome.
College at Irvine, Smith College near Hampshire. And this project started when I was an MA student at Oxford studying with P.S. Anderson, who's a philosopher. And looking at these ethical cases, I thought, these are just justifications that don't actually matter if we're considering the ethical value because they don't reflect the speaker's opinion. And Professor Anderson said, that would be a great dissertation topic, and you are going to Berkeley rhetoric, because that's where you can do it. So it's been quite a path around the world.
So did your father also work in rhetoric or a similar field, or is he a nuclear physicist or something?
I also couldn't get away from my family legacy, and I'm still in the humanities.
So are you glad to be back in California then?
Of course. Aren't we all?
Well, so, you know, sometimes I hear sort of opinions about, well, it would be nice if there were more housing. Okay, I think our judges are finished. So thank you very much, Lilith. We now move to our 8th contestant, Joe, is it Charbonnet?
That's right.
So Joe is in his 5th year in the PhD program studying environmental engineering, which is something that is important for all of us. But we'll get to that.
When was the last time you stepped in a nice, deep puddle? If it was a real sock soaker, you probably viewed urban stormwater the same way our municipal leaders have for a long time, as a complete nuisance. You see, stormwater can overflow combined sewers and flood residents' basements, so cities generally try and be rid of it as quickly as possible. And this is all good and well, especially in places like Berkeley, where we get our water from nearby mountain reservoirs. But in places like LA, where they spend hundreds of millions of dollars importing their water, fresh water literally falling from the sky starts to look pretty darn good. The problem is, in addition to water, our gutters contain herbicides and pesticides, metals from our brake pads, and yes, even dog food. These hazards hold back the potential use of stormwater, and they're why I've invented man-sand filtration media. Now, it's not called man-sand because it got nervous and forgot to shave this morning, but because it's made with a naturally occurring mineral called manganese oxide, which is actually capable of removing some of the contamination in stormwater. You see, 30 or 40 years ago, the soil scientists discovered that manganese oxide has this really interesting property where it can absorb and destroy certain other chemicals, and they noted how interesting this was for the redox cycling of transition metals. But now I'm going back and looking at this data and saying, wait, the potential for an engineered application here is amazing. By coating sand with manganese oxide, it's like giving it superpowers. Endocrine disruptors like BPA can be oxidized, while toxic metals like lead are absorbed like a chemical sponge. And these properties are rechargeable, meaning once the man-sand reaches the end of its life, it can actually be regenerated without having to be excavated, which saves cities a ton of money. In California, we like to store our water in underground aquifers. The man-sand fits into the existing infiltration basins cities are already building to recharge these aquifers. However, it uses cutting-edge chemistry to turn the stormwater into a viable drinking water resource. This ease of installation has enabled us to set up field sites with interested utilities from Sonoma all the way down to Burbank. By helping to unlock the full potential of stormwater, This technology can help to liberate places like Southern California from expensive imported water, which uses 5,000 gigawatt hours of electricity each year as it's pumped up and over a mountain range. I tell that statistic to engineers and they think, wow, that's 20 million tons of CO2 emissions. But if I tell it to a municipal leader, they think, wow, that's over $300 million. The point is that by turning what was pollution into a natural, low-cost solution, this technology helps cities save their rain for a sunny day. Thank you.
Thank you so much, Joe. I will resist the temptation to dive into the chemistry.
Well, I think that one thing that people might be interested in knowing is one of those plucky soil scientists way back when that was studying transition metal oxides was actually you. So in science, when we say we stand on the shoulders of giants, that's you. So.
You're being too kind and flattery of me. We're not getting you anywhere with the judges. But thank you very much anyway. So how did you get involved in this? Sort of, you obviously bring a lot of passion to the field. Sort of, for those who don't know, sort of the kind of origins of Joe's field was originally kind of sanitation engineering, which you know, is sort of basically described as what happens after you flush. So it's not necessarily the kind of area that really necessarily grabs people. But clearly, I mean, it's really, really important for all sorts of reasons. What was your story in terms of getting excited about it?
Yeah, well, I've always really been captivated by water. I think water is
it's the coolest thing.
It is. I think it's really telling that across cultures and creeds, everywhere you go, water is this symbol of rebirth and change and rejuvenation and life. And I think it has this sort of primal, vital force around it.
Probably because a lot of our bodies are composed of it. Yes.
Exactly. And so the idea that you can study that and engineer around it and learn how water is the language that writes the world around us has always really appealed to me.
And did you grow up in California?
I actually grew up in Florida.
Okay.
And I was fortunate. My mother is a sixth grade science teacher, and so I grew up with science all around me. We'd hear about something on the radio, and then run out and buy a pack of gummy bears and run them over with a car to learn about elasticity. And so I was really fortunate to have a strong force in my mother that made me curious and inquisitive about the natural world.
I'm glad somebody else was scarred, and not just my, not just my children. Sort of in the area of civil engineering, one of the things that you'll appreciate is that my kids were tortured. They would come and say, "Mom, I fell down on the cement and scraped my knee," and I'd say, "No, you didn't." And they'd say, "Yes, look, it's bleeding." I'd say, "Yes, you fell down, but it was on concrete. It wasn't on cement."
There's aggregate in there.
That's right, yeah, so you'll appreciate that. But I'm glad somebody else suffered. I'll have to tell my kids that they were not alone. Thank you very much, Joe. And continuing on the environmental theme, really this randomization was clearly very random and not planned. Our ninth contestant is Tomas Lyon, who is in his fourth year as a PhD student in environmental health sciences. So, Tomas, please give us your 3-minute talk.
Doing public health research with impact is really challenging because it's so hard to change individual behaviors. We smoke too much, we drink too much, we eat too much. Now I know this from my New Year's resolutions around exercise. They've all gone out the window while I've been writing my dissertation. But in public health, we focus more on changing the environment and on encouraging healthy behaviors. So that means choosing water over the beer or salad over the steak. Yeah, we can be real killjoys as friends sometimes. But I focus on the physical environment the air, water, and soil. And specifically for my research, I've worked in Northeast Thailand on a worm called a liver fluke. We care about liver flukes because they cause a very fatal form of cancer known as cholangiocarcinoma, which is very difficult to treat. Now, people get this worm by eating raw or undercooked fish, and in Thailand, that's a very deeply embedded local cultural tradition, so that's hard to change. So I work on the environmental side with the hosts in the environment, which are very small snails and local carp fish species, and I ask the question, where are they in the environment, and where are they getting infected? Now, on top of this environmental data, I work with professors and government officials on a control program over the last decade that has followed the cohort of 10 villages shown here to show that fewer people are getting infected with the parasite. But the question is why? Is this because of drug treatment? Is this because of development? Is this because of changes in the flooding cycle? And so using this environmental data with the disease data together, I use it to reconstruct changes in environmental transmission over the time to understand what's been happening. Now, on top of all this, I've done a lot of field and lab experiments. So you can see me here with some fish ponds. And I've done fish pond experiments about if we change the source of water and the water quality, how does it affect how many parasites a fish get? I've also looked at doing surveys of the snails and fish, and I've done flood modeling to understand where the snails and fish and the parasite itself goes in the environment to understand how it moves around. Now, we can use this approach not just for liver fluke, but for any disease. Take malaria, for example. We don't understand well how far a mosquito flies over a landscape, but if we can leverage environmental and disease data, we can get insights into those processes. And the outputs of these kind of data are useful for designing really effective public health control programs, so we can time them appropriately through the year, and we can do it in locations and villages where we're going to have the most impact. And all this is important because we want to reduce disease, we want to reduce cancer, and we want a healthier world. So next time, when you're at dinner with your public health friends, we're not just nagging you, we're trying to create a healthier world for all people. Thank you.
So it must be incredibly rewarding to see places where the incidence of parasites is decreasing. But what got you interested in parasites? I'm going to ask this question. It's kind of, it always feels, yeah.
So I did my undergrad in environmental engineering at Georgia Tech with Joe, actually, and thought a lot about water, too, which is really great. And when I came to Berkeley, I worked with my advisor, Bob Spear, who is another engineer who crossed over into public health. And so we think about that systems approach about water systems and how we can make changes in the environment to reduce parasites. And frankly, parasites just have a really interesting life cycle. They're very complex, and they're really evolutionarily very interesting.
So are there parts, you showed a very encouraging graph of locations where the parasite or the infection rate was decreasing. Do you think that we're actually ever going to be able to eliminate human parasites in the way that humanity's been able to eliminate diseases, like smallpox? Or do you think that actually there will always be certain parasites? And then there's the very interesting question of, would there be unforeseen sort of ecological ramifications from elimination of certain human parasites?
Certainly. So two things going on. One is that in environmental health, the last mile is really difficult. And so with a lot of parasites, we reduce it down to 10% or less percent of the population that has a parasite, but it's really hard to get that last fraction out because these are high-risk people. They may have risky behaviors. And the thing about parasites is, as probably a lot of people know from popular science, is they have some beneficial effects on your immune system. And so actually, this parasite, we've seen protective effects against diabetes as Thailand develops and people get more obese. Actually, there could be parasite benefits to things like that. So it's a very complex problem, and there's a lot of trade-offs. But certainly, we want to reduce cancer, which means reducing parasite loads.
So the actual situation of actually eliminating them is just really not going to happen.
It's going to take a long time, and I think it's going to happen in, like all public health efforts, in concert with general development, with improvement in water sanitation, with economic opportunities, agricultural change. So.
And do you see an emergence of big data approaches to studying problems like this?
I've thought about this a lot because the kind of data I have is very fragmentary, and so it'd benefit from a lot of sensors, big data approaches. But frankly, the poor are always going to disproportionately yield the burden of infectious disease. And I think development would precede big data coming to large chunks of the population. Certainly some efforts can help, but long term, we got to do development. We got to improve everybody's lot altogether.
Okay, well, thank you very much. And our final contestant, who's been nervously sitting through the other 9 talks, she just happened to draw that straw, is Sylvia Lewin, who is in physics in her 6th year of the PhD program. So we look forward to what is our last of 10 fascinating talks.
When a guitar string is pulled out of place, there's a restoring force that pulls it back. That starts a regular vibration back and forth that we hear as a note. The frequency of the note depends on the chord's length and thickness, its density, and its elasticity, how strongly the chord pulls back when it's pulled out of place. In general, every object can vibrate in many different ways, expanding and contracting, twisting, bending. And each of these types of vibration will have a specific frequency related to the object's size and shape, but also how elastic it is, how strong a restoring force pulls back when the object is deformed in these different ways. At the atomic level, elasticity is related to the electronic bonds holding a material together. So elasticity can tell us a lot about what is happening inside a material, not just its physical structure, but things like magnetism as well. It turns out that by measuring the natural frequencies of an object and knowing its size and shape, we can figure out its elasticity. My research is all about using this technique to understand unusual materials. Materials like superconductors that can conduct electricity without any resistance when they go below a certain temperature. That's a pretty incredible property. It means they don't lose any energy to heat, and once an electric current is set up in a superconducting loop, it can persist almost indefinitely. This makes them, for example, great for powerful, cheap, and stable electromagnets. Most MRI machines in hospitals around the world rely on superconducting electromagnets. Some common materials can become superconducting at low enough temperatures. For example, aluminum becomes superconducting at 1.2 Kelvin, less than 2 degrees above absolute zero. For context, that's negative 457 degrees Fahrenheit. We can reach those temperatures in the lab, but it's not easy. On the other hand, a few decades ago, scientists discovered some complicated compounds that begin superconducting at temperatures more like 90 Kelvin. That's still quite cold, but it's much easier to achieve. So these so-called high-temperature superconductors can be used in a variety of practical applications, from the next generation of MRI machines to magnetically levitated trains to transmission of electricity across the power grid. Our dream is a room temperature superconductor, but there's a problem. We don't actually know how high temperature superconductors work. In order to engineer and manipulate new materials with the properties we want, we have to understand why these materials have the properties that they do. My contribution is to measure the natural frequencies of high temperature superconductors and analyze how their elasticity changes as I take them from room temperature down to almost absolute zero. From this, I can obtain a great deal of information about what is happening within the material and what other changes are taking place besides the material becoming superconducting. This could revolutionize our hospitals, our trains, and our power grid itself. Thank you.
Thank you so much, Sylvia. So I have to say that I know you didn't intend this, but you made me feel very old. Because I remember I was younger in my career, but I was still on the faculty at Berkeley when these developments that you've alluded to several decades ago happened. Actually, I think you said a few, and it was only a few, but it was still a long time ago. And I was sitting listening to you and thinking, right, there was so much sort of buzz about the high temperature superconductors. I remember it all very well. And then everything seemed to go quiet. So what sort of attracted you to this kind of old field of physics?
Yeah, things went quiet because people realized it was a lot tougher problem than they had thought when they started.
Yes.
People thought that we would be able to understand this right away and take advantage of it. And it turns out to be really tricky, but that's what attracts me to it, because these materials are so complicated. There's so much going on inside them that it's great to be able to work with scientists, who are working around the world. It really has pushed forward experimental physics in a lot of ways. People are trying to invent new techniques just to study these materials in some cases.
Mm-hmm. And are you doing experiments, or are you a theoretician kind of interpreting other people's experiments?
I'm doing the experiments, but what I really like about this project is that there is also a lot of analysis involved. So I get to do the hands-on work, but also a lot of math and a lot of programming. I get to do it all. Great.
And so, sort of what drew you to this particular area of physics, or physics in general? Did you sort of always want to do physics as a kid, or were you somebody who just sort of stumbled on it in college or something?
I guess you could say I stumbled on it in high school, because I had to take a physics class, and up until that point, I hadn't been very interested in science, but I really liked math. So once I learned that you could use math in science, that was a revelation. And, and there are many other fields that use math in science as well, but not so much at the high school level.
Yes, and suddenly it goes from being a mystery to something that you can actually calculate and work out physics. And did you grow up in California or somewhere else?
No, I'm from Delaware originally. So coming here for graduate school was actually the first time I lived off the East Coast.
But it's all right.
Oh yeah, I really enjoy it here. But I do miss the snow. Unpopular opinion.
You actually don't have to go back to Delaware. You can actually just go to the Sierra. I was skiing on it over the weekend, so it's not that far away. All right. Linda's saying that the judges are done, so thank you very much, Sylvia. All right, so now is the time that everybody gets to do their voting for the People's Choice selection. So you've got your ballot. Please complete your ballot. And Sharon at the back there has a big basket, which is where you drop your ballot. We're now going to break for about 30 minutes, hopefully slightly less than that. We have some light refreshments for everybody except the judges. And the judges are going to go off and work hard. Liz is going to take care of the judges, right? And so I'll see everybody back here. And I'm going to talk about some of the technical details. To our judges. I said at the beginning that they were going to have a difficult time of it. I think everybody who is in the room realizes that was an underestimation. They must have had an incredibly difficult time. I was so impressed by all of the contestants. So thank you very much, judges, for making a difficult I would also be remiss if I didn't thank all of, well, first of all, John and his team. Thank you. You selected some fantastic semi-finalists. I'd also be remiss if I didn't extend sincere thanks to all of my colleagues in the graduate division who've worked so hard to put on this event. One of the things that I didn't realize is that we were actually being streamed into another room because there was so much demand to see what was going on. So there's a lot of work that goes on. So please join me in thanking everybody who put this competition on. And a particular shout out to Linda Louie, who's new graduate division staff. She just finished her PhD, so she knows what it's like being on your side of things. So thanks very much, Linda. All right, and many thanks to all of the contestants for doing a fantastic job. I heard that you worked very hard on polishing up your presentations. I thank you, but I also know that that is a skill, some professional development that will stay with you for your lives. But in addition, all of the competitors today will receive $100 each for advancing to the semifinals. So congratulations to all of you. All right, I am going to be announcing winners and giving certificates, and I believe that the actual monetary awards will be done in an extremely unglamorous way, like payment to your car's account or something like that. But it will happen. So without further ado, I'm very pleased to invite our third place winner up, Kelsey Adame. Congratulations. Well done. Our second place winner, Daniel Drew. Congratulations. Congratulations. And our first place winner, and for that we have a list. This is the car's account. Joseph Charbonnet. Congratulations. Congratulations. So he is going to be it at the major competition. And the People's Choice Award, Joseph Charbonnet. Congratulations. So thank you so much, everybody. You've been a wonderful audience. I hope that you come back next year. And students, tell your colleagues about how much fun this is and encourage them to participate next year. Thanks very much, everybody.